Okay, so for this first one, it says about 7% of men in the United States have some form of red-green color blindness. Suppose we randomly choose 4 US adult males. What's the probability that at least one of them is red-green colorblind? Design and carry out a simulation to answer this question. So for this one, the first thing I need to do is out of 4, if 7% are colorblind out of the 4, there's a 20, so I did 4 times 0.07. So there's a 28% chance that one of them would be colorblind, So that's what I'm going into this thinking. So in this one, I'm going to go through, that's the actual, that's kind of what I'm doing actually, but the way that I'm going to simulate it is this way, and you guys don't need to have this first part, but this is how I would simulate it. And I want you to do 10 trials. So a simulation would look like this. I would label the colorblind 0, 0 to 06. That's 7 numbers. And then I would number the not colorblind 07 through 99. That's 93. The other 93 numbers, or 93% that are not colorblind. So what we're going to do now is I'm going to go to table line 105. You guys can go to whatever one you want. And I'm going to take 4 people at a time and then count how many I have that have a colorblind person in them. I'm going to repeat that 10 times. So in my first simulation, I take on that line, I go straight across and I have 95, 59, 29, and 40. I don't have anybody in there that are between the numbers 00 and 06. So I have no colorblind. I do that 10 times to show taking 4 people with a 7% chance, and I actually got none in my sample. I got none. After you guys simulate that, and you do need to show me the simulation for credit, I actually had none. The actual probability is 28%. So what I would expect in this case is that if I had done 28 times of this, and I only did 10, just to get a feel for it, but had I done this 28 times, I would expect one of those, or if I did it 100 times, it's better to think of it this way. If I had done this 100 times, I would expect about 28 of them to have somebody that was colorblind within them, within the numbers. So that's how you're going to run your first one. I'm interested to see if you chose a different line. I encourage you maybe to not use line 105, use a different line to figure out if you can get one that does have a colorblind, that has the number 00 through 06. Moving on to number 12, it says tossing a coin 3 times. It says, what is the sample space for this? Well, I decided to look at kind of that idea of like heads, 3 heads, 2 heads, 1 head, and then no heads simulation. So I could toss a coin 3 times and get heads every time, or tails every time. And then the only other option is to get heads twice, but there are different ways that that can happen. Like I toss, I get a heads, I toss, I get a heads, I toss, I get a tails. Or I toss, I get a heads, then the second toss, I get a tails, and then the third one, I get a heads. So there are different ways that both of these events can happen. That's how I like to list my sample space for this. It's better to do this, and I should have done this. Sample spaces, we put an equal, and then we do this right here, these kind of curly brackets right there, and that is a sample space. In B, it says, now assign the probabilities. Well, the probability for all 3 heads, or you could really say all 3 tails, it doesn't really make a difference, is 1 out of the 8 different times. 2 heads, 3 out of the 8. 1 heads, 3 out of the 8. And no heads would be 2 out of the 8. I'm sorry, 1 out of the 8. There's only 1 time. Okay, so that would be the probabilities for each one of those. And you could have chosen tails instead of putting heads like I did, but the probabilities will all be the same. I want to remind you that going into this, I knew that there would be 8 outcomes because I always take how many outcomes there are on the first toss times the second toss times the third. Okay, it's always multiplying. 2 times 2 is 4, times 2 is 8. I knew going into this that my bottom number would be 8 because there are going to be 8 different outcomes. Okay. In number 13 here, we're talking about blood types. It says, what is the probability of having an AB blood type? Because look it's a question mark in here. Well, in order to get that, I know that all my probabilities have to add up to 1 or 100%. So I first add these to see what I get. And I end up with 96%. If I add 49 plus 27% plus 20%, I get 96%. It would mean that I'm going to take 1 minus that. That's known as a complement, by the way. I'm going to take 1 minus that to get 4%. It has to be 4% right here because I didn't add up to 100%. I was almost there. I added up to 96%. But AB blood is actually the most rare, and only 4% of the population has AB blood. In B, it says, what is the probability that a person chosen does not have AB blood? Well, that's that 96% that we just got. And in my last one, Maria has type B blood. She can safely receive blood transfusion from people with O or B. So I'm going to go up here and I'm going to look at these two, O and B. That's 69% when I add those together. That's known as the addition rule. Okay, O and B, I'm going to add them together. She has a 69% chance of getting blood from somebody that has O or B. Okay, number 14. Education in young adults. We're going to choose a young adult age 25 to 29 at random. The probability is 13% that the person chosen did not complete high school, 29% that the person has a high school diploma, but no further education, and 30% that the person has at least a bachelor's degree. What must the probability that a randomly chosen young adult has some education beyond high school, but does not have a bachelor's degree, and why? Okay, so in this one I knew, okay, I must have to add these up and see there must be a missing component here. I added 13% plus 29% plus 30%, okay? And I got, let's see, 72%, which means that 1 minus 72%, 28% were in between these two. So we have 13% that did not graduate high school. We have 29% that got a high school diploma and 30% that got a college diploma. It means that we have our 28% that had some education after high school. In B, it says, what is the probability that a randomly chosen young adult has at least a high school education? At least a high school education. Well, that's that 29% and above. So that would be the 29%, the plus the 28% we just found, plus the 30%, which is 87%. The other way to think about it is to do 1 minus the probability of not having a high school education, 1 minus the probability of not having a high school education, which would give us our 87%, our 87%. What rule is that? I use the complement rule. The complement, if I put 1 minus this, that's known as the complement rule. If you added instead, you added 29 plus the 28 plus the 30, then that's known as the additive rule or addition rule. Okay, and the last one, we have all the following breakdown for 20% currently undergraduate in business, 15% undergrads in a other field of study. We have 60 that are graduates and employed, and 5% that are graduates but not employed. It says, what is the probability that the customer is currently an undergraduate? An undergraduate. Well, we have two different subsets of undergraduates. We have these that are undergraduate business and 15% that are undergraduate students in other fields. I had to add those two together and we get 35%. Those were both my undergraduates. That's known as the addition rule, okay, or additive rule. Either one is fine. The next one says, what is the probability that the customer is not an undergraduate business student? Okay, well, the way I did that is the only ones that are undergraduate business students are these 20%. So I'm going to take 1 minus that 20%, which means 80% are not those people. That's known as the complement rule. The complement rule. When you do 1 minus something, and we're going to cover that more tomorrow, but that's known as the complement rule. It's 1 minus whatever probability. And that is all for that.